Hello and welcome to this tech talk on optimizing Lambda performance for your serverless applications. My name's James Bezic and I'm a senior developer advocate here at AWS Serverless. Prior to this, I've been a software developer and a product manager for many years, and I've worked in a variety of startups and larger enterprises. I'm a self-confessed serverless geek, and I've built a number of large applications using entirely serverless technology. So feel free to contact me anytime with your serverless questions, whether you have questions from today or you have other general questions around serverless development. You can reach me via email or Twitter anytime. So all of the slides from today will be available to you after this webinar, and you'll also be able to watch this webinar again as a recording later. So we're going to cover three topics today: cold starts and what you can do to avoid them, memory and profile and Lambda functions, and architecture and best practices. Before we get started, let's just review how Lambda works under the covers. This is a 300 level webinar, so this will be very quick as a recap. Lambda is designed to run your code on demand in response to events. Now, if we look at the anatomy of a Lambda function, there are several different layers. Going from the outermost ring, first there's the Lambda compute substrate, the underlying compute for Lambda. Next, there's the Lambda service itself, which manages the scheduling and organization of workloads across hundreds of thousands of customers. Now, both of these layers are completely invisible to customers and managed entirely by AWS. A little further up, there's the execution environment. This is customer specific and AWS account specific. It's the secure place where the code itself is run. In each execution environment, there's a language runtime. Lambda provides a range of supported language runtimes, including Node.js, Python, Java, .NET Core, Go, and Ruby. You can also bring your own runtime, and there are customers running PHP, Rust, C++, Erlang, Perl, COBOL, and many other types of language runtime. Lambda itself is agnostic to your choice of runtime and has no inherent preference for one runtime over another. Finally, there's your function, the code you provide, zipped up as a package with any dependencies needed. The execution environment and runtime is instantiated on demand for scale events, and the function is instantiated for every request. In this case, everything inside the handler is considered part of the function, and everything outside of the handler is considered an initialization call and run alongside with the execution environment initialization. So from these 5 layers, these are the 3 where you can make decisions that impact performance. Everything I'll be talking about today is focused on these layers. It's worth mentioning from a performance perspective that the AWS Lambda team is continuously working to improve performance on the invisible layers, so you get the benefits of these improvements automatically as we release those upgrades. At the function level, there are a few different elements. The handler itself, which is the function which will be executed upon invocation, and then these are the parameters that are handed into the function. You have the event object, which is a JSON object describing the event causing the invocation. It's an array and can contain multiple events. And then there's the context object, which provides methods allowing you to interact with the runtime and the execution environment. You'll notice above the handler that these are the function's dependencies, configuration options, helper functions, and so on. And here is where functions might initialize database connections, for example. All of this is static initialization or init code. Putting this all together for when an invocation occurs, this is the function lifecycle within the Lambda service. When a request arrives for the first invocation of your function, Lambda will first download your code onto the part of the compute substrate where your code will execute, and start a new execution environment that's sized based upon your function allocation. Then it will instantiate a runtime and then execute your code. This environment is kept alive for some window of time, depending on your traffic patterns. When a function is first run, all of these events happen. This is what is commonly called a full cold start. If another request arrives, only the handler is executed again, and this is much faster. This is a warm start. The first 2 steps are optimized by AWS, whereas the last 2 steps can be optimized by the developer. If you want to start measuring performance in a systematic way throughout your serverless applications, One of the services that can really help do this easily is AWS X-Ray. There are a couple of different ways to do this. First, in the Lambda console, you can check the active tracing box in the X-Ray panel. After you save the changes, the console adds permissions to your Lambda function to enable X-Ray integration. Second, you can use the SDK. When your application makes calls to microservices or public HTTP APIs, you will need the SDK. The SDK also allows you to make custom annotations and record additional metadata by using the code on the slide. There are SDK calls for both synchronous and asynchronous function invocations. As data is collected, X-Ray provides a visualization for invocations as they move between AWS services, and this makes it much easier to identify areas for performance optimization. At a function level, you can use X-Ray to drill into the duration periods of an invocation. This example shows an asynchronous Lambda request with one successful invocation and one downstream call to DynamoDB. Here you can see the dwell time. This is the time spent in the Lambda service queue, and it shows the time for that first attempt. If there are more than one attempt, then each attempt to execute the function is in a separate segment. At the function level, it shows the init code, and that's the static initialization code run before the handler. And then it shows the time taken by other AWS services used. This granularity is important for performance optimization and informs you where you can start looking to make improvements. So that's a very brief overview of the Lambda service and the distributed tracing system X-Ray. In the rest of this webinar, we're going to get deep into performance optimization. I'm going to cover 3 areas of performance. The first is latency. Here we consider the entire round trip time, which is the overall user experience, and we'll go deep into cold starts. The second is throughput. This is the total number of transactions processed. And the third is cost. We're looking at reducing the overall spend on an application. So let's get into cold starts. If we peek under the covers of the Lambda service, there's a distinct difference between a cold start and a warm start of your function. All requests come into the Lambda service via the Lambda API. The Lambda service first checks to see if a warm execution environment is available. If this is the case, it means the function has been executed previously fairly recently. And when this happens, this is called a warm start because the execution environment is ready. Next, Lambda invokes the handler and completes the execution. So how is this different to a cold start? Well, in a cold start, since there's no warm execution environment available, there are additional steps needed. First, the service must find an available compute resource and then download the customer code. It starts and prepares the execution environment and then executes the init code. That's the code outside of your handler. Finally, invokes the handler and completes the invocation. There are some important things to know about cold starts. First, cold starts affect less than 1% of all production workloads. This is important since you'll often see cold starts more often in development since you execute the function less often. In production systems where functions are usually invoked more frequently, they are less common. We optimize to make sure that cold starts are rare. When cold starts do happen, the time taken varies from under 100 milliseconds to over 1 second. Now, a couple of things to keep in mind here are that you cannot target warm environments. There's no mechanism for doing this. So there's no affinity for repeat requests or any concept of sticky sessions. This is all managed for you by the Lambda service. Also, some of the community have developed libraries for keeping functions warm by pinging them with CloudWatch events. Now, this is fine if you want to increase the likelihood of hitting a warm environment for infrequently used functions, but it's not a guarantee, and it doesn't help with cold starts when functions are scaling up or if the execution environment is load balanced to another availability zone. So if you really need a guarantee of a warm environment, a better approach is to use provisioned concurrency, which I'll talk about a little later. Cold starts are caused by a number of different events. Warm environments don't stick around forever. We regularly reap them every few hours to keep execution environments fresh. It's possible that you can run on resources that encounter failures. So in that case, the next time it's run, you'll see that there's a cold start. On occasion, there are warm functions that are ignored in order to rebalance load across availability zones. Now, Lambda is a multi-AZ service where the load balancing is managed for you. Also, anytime you update your application code or change your function configuration, this will lead to the existing environments being flushed, and the next invocation will also be a cold start. Finally, there's scaling up. The Lambda service will scale up when there's more work to be done, and each time a new concurrent execution environment is started, that environment is started afresh, and it will be a cold start. AWS optimizes for this part of the cold start, the setting up of the execution environment, but it's influenced by 4 factors. The first is the memory allocated to the function. You choose between 128 megabytes and 3008 megabytes. Typically, functions with more memory allocated are reached less frequently. Second, the size of the function package impacts the time taken for the service to download the code. Larger packages are basically slower to download, so making your packages as small as possible can help here. Next, how often the function is called influences how long it is kept warm. Remember, environments are reaped every few hours regardless and load balanced across different AZs. And that still happens even if there are warm containers. But generally speaking, functions used more frequently will be hitting warm environments more often than those used less frequently. Finally, we use internal algorithms that are proprietary to how the Lambda service optimizes customer workloads, and these are a big factor too. We make changes to these regularly to provide a better experience for customers. One major improvement I'd like to mention is the work we've done to improve cold starts for Lambda functions running inside customer VPCs. Customers frequently run functions inside of a VPC to access services like Amazon RDS or Elasticache or Elasticsearch or EC2 or ECS. Now, using AWS Direct Connect, customers can also connect to on-premise resources using Lambda with VPC connectivity. During the last few months of 2019, we started rolling out some major changes to the way Lambda functions work with your VPC networks. When you configure your Lambda function to connect to your own VPC, it creates an elastic network interface in your VPC and then does a cross-account attachment. Previously, the creation of this ENI happened during the invocation process, so it could add a considerable amount of time to the cold start. It also consumed resources such as precious IP addresses in your VPC subnets. So as your functions scaled, you had to be mindful of managing IP address space in your subnets and reaching the account level network interface limit. So after these improvements were rolled out, this process changed considerably, and there are 2 noticeable impacts. The first is the dramatic reduction in cold starts, and the second is the more efficient usage of network resources, thanks to the use of managed network resources. As you can see in this example on the slide, one entire invocation was reduced from nearly 15 seconds down to under a second after these changes were rolled out. These VPC network changes have now been rolled out to all public regions, and you don't need to do anything in your code or do anything special to benefit from the reduced cold start times. So to learn more about these changes, take a look at the bit.ly link on the screen. So that's the execution environment portion of a cold start. Now let's look at the second component of a cold start that's caused by static initialization, or the init part of your code outside of the handler. The code that runs outside of the handler is frequently used to import dependencies, set up configurations, and initialize connections. This is run before the Lambda function at the initial start of the execution environment. And we have run analyses on Lambda performance, and the data shows that the longest cause of delay before handler execution comes from the init or pre-handler code. So in other words, the section that developers can control the most can also have the biggest impact on the duration of a cold start. This part of a cold start also occurs when a new execution environment is run for the first time, and also when scaling up. In this portion of the cold start, it's entirely influenced by only a couple of things. First, the size of your function package in terms of imported libraries and dependencies and Lambda layers. It's really important to be efficient in importing only what you need. Next is the amount of code and the amount of initialization work. The key thing to remember is that execution environments are reused. So what can you do to optimize here? Well, if you find yourself with many objects and connections, it might pay to see if you can re-architect into smaller, more specialized functions. Sometimes this is a good approach. It's important to import only what you need, so trim down SDKs and other libraries to the specific parts required. Pre-handler code is great for establishing connections to downstream services like databases, but be prepared to then handle reconnections in further executions. Also, lazily load the variables in the global scope. Don't load it if you don't need it, and also then clear out any use variables so you don't run into a leftover state. Having said this, there are workloads where there's a limit to how much you can optimize any of these things. And if you really need to completely eliminate the cold start problem, but still be able to use large libraries of code and lengthy static initializers, then provisioned concurrency is the solution. Provisioned concurrency is a new feature announced last year during reInvent. This works by pre-creating execution environments ahead of usage, all the way up to running the init code. It's really easy to use. All you need to do is specify the capacity, in other words, the number of execution environments, and when you want to use them. You can set this up in the Lambda console, in CloudFormation, and in SAM, the serverless application model. It's mostly useful for interactive workloads that are heavily latency sensitive, reducing the time to running the function handler to double-digit milliseconds. It offers greatly improved consistency all the way through the long tail of performance at the P95, P99, and P100 levels. If you go back to our function lifecycle flow, this is what happens when those execution environments are pre-created. First, the function is configured to use provisioned concurrency. Next, Lambda finds the available compute resources for the capacity requested. It downloads the customer code into all of those execution environments and starts and prepares the environments. Most importantly, it executes the init code. So what's interesting here is if you consider both components of a cold start, the creation of the execution environment and the running of the customer init code, both here are addressed by using provisioned concurrency. Since the environment is prepared in advance for the function usage, you no longer need to be concerned by the time taken for your static initializers. After the execution environments are prepared with provisioned concurrency, every function invocation follows the path above. You'll recognize this flow from the warm start earlier, so every invocation in provisioned concurrency is a warm start. There are a few things to know when using provisioned concurrency. First, it reduces the start time to double-digit milliseconds, and you'll see this in the X-Ray reports if you use X-Ray for tracing. PC can only be configured on a published version or alias of a function, by the way, and not on the latest version of the function. Some customers use very large capacities, so it's important to know that provisioning ramps up at a rate of 500 per minute. Bear this in mind if you need 5,000 execution environments, since it will take 10 minutes. Beyond configuring the PC-specific attributes, there's no actual change to your Lambda code or handler. Also, if your usage goes above the PC capacity, that's no problem. All of the requests over this number will use regular on-demand Lambda. Invocations in this overage follow the usual on-demand Lambda behavior. Regardless of how you configure provisioned concurrency, overall account concurrency limits per region still apply. If you need higher levels of concurrency, please open a support ticket with us and we can accommodate you. Provisioned concurrency is also in AWS tools like CloudFormation and SAM, and in partner tools like Serverless Framework, Datadog, and Thunderer. So it's broadly supported in tools and services you might already be using. In order to maintain availability and help with scaling, we provision more resources than you request. You don't pay for these extra execution environments, and because they execute init, they could consume other resources from your account, such as database connections and calls to other services. If you're logging in your init code, you will see this extra capacity in CloudWatch logs. To keep execution environments fresh, we still reap them regularly, but we'll pre-create execution environments behind the scenes. So you'll see inits in your logs every few hours without configuration changes or other events. This doesn't impact performance. You'll always maintain the total level of capacity that you requested for the function, even if we're reaping and pre-creating in the background. For on-demand Lambda, init code receives a CPU burst that is typically higher than when the function handler is run. This is not the same in provisioned concurrency. We give less CPU burst to provisioned concurrency than on-demand Lambda during the init phase, and so code could take a little longer to execute. Setting up provisioned concurrency in the console is pretty straightforward. Once you've published the function version alias, navigate to that version in the provisioned concurrency panel. Here you can specify a capacity. Once you save the new setting, the status shows up how much capacity is provisioned, bearing in mind the 500 functions per minute ramp up. Once it's completely provisioned, the status is updated. It's possible to assign provisioned concurrency capacities to different versions of the same function. This is the process used to set a fixed or known amount of capacity to a given function version. But if you don't know what capacity to set, or you need some assistance in setting capacity, there's another option, and that's application auto-scaling. So you can use this option through the CLI or through CloudFormation, but it's not directly in the Lambda console. You set a minimum capacity and a maximum capacity together with a target utilization. The service will then respond to changes in demand and scale your provisioned concurrency appropriately. Remember that the 500 execution environments per minute ramp-up limit still applies, so for extremely heavy load, it pays to set the minimum capacity at a higher level to ensure that you have enough capacity to meet the demand. The usage of provisioned concurrency configured this way can be monitored via CloudWatch metrics, where you can see how many environments are provisioned and the utilization level. The second topic for today's webinar is memory usage and profiling. The most important lever that you have available in a Lambda function is memory. Lambda exposes only a memory control, and you can select between 128 megabytes of RAM and 3008 megabytes for your function. But memory is more like power, because as you increase the memory, this proportionally increases the amount of CPU core and network capacity allocated to the function. Many developers leave the memory set to the default 128 megabytes, and this is fine for very simple functions. But if your code is CPU, network, or memory bound, then changing the memory setting can dramatically improve performance overall. In fact, it may even be cheaper. Let me show you. Here's an example of a CPU-bound function. It computes all of the prime numbers up to 1 million. Now, when allocated 128 megabytes, this takes 11.7 seconds. As we increase the memory at 256 megabytes, that drops to 6.7 seconds. And then it drops to 3.194 seconds for half a gigabyte. And finally, at a full gigabyte, it only takes 1.465 seconds. So while it's probably no surprise that it's faster, what might surprise you is that the costs are about the same, within 1,000th of 1 cent. Why is that? Well, Lambda billing is based on gigabyte seconds, so you can find that more memory is sometimes cheaper if the overall execution time is substantially less, or at least the cost might be comparable, as in this example. Obviously, running tests on every single function with different memory allocations is very time-consuming, so fortunately, there's an automated way that you can do this. AWS Lambda Power Tuning is an open-source tool that can help you visualize and fine-tune the memory and power configuration of Lambda functions. It was created by our very own Alex Casalboni as a simple way to find the right balance of memory, speed, and cost in an automated way. The application itself uses AWS step function state machines to run multiple concurrent versions of your function at different memory allocations and measure how they perform. The input function will be executed in your AWS account, and it performs real HTTP calls, SDK calls, cold starts, etc. The state machine also supports cross-region invocations, and you can enable parallel execution to generate results in just a few seconds. You can implement a CI/CD process around this too to automatically run this analysis as you build new functions. In addition to the GitHub repo shown here, you can also find this app in the serverless application repo. Just search for power tuning and then click deploy. It supports 3 optimization strategies: cost, speed, and balanced. The power tuning app only requires a few parameters to start. The Lambda ARN identifies the target function. The power values specify the memory allocation amounts you want to test. Num sets the number of iterations, and that's the number of times that your function will be run at each level up to 100. A larger number here can help smooth out average values. And then there's an optional static payload that will be used for every invocation. There are also many other input parameters to enable optional features. If you want to test your function against every available memory range in 64 megabyte increments, specify all in the power values parameter. By default, this application runs tests sequentially. This ensures that your function calls are fair to other resources and creates a measurement of the execution time. Alternatively, you can have all of the tests run in parallel using the parallel invocation flag. Depending on how many iterations are set in the num parameter, you may find that these executions are throttled. Another optional parameter is strategy. This can be set to cost, speed, or balanced. The default value is cost if you don't supply a value. Now, if you use cost, the state machine will suggest the cheapest option, disregarding the performance. While if you use speed, the state machine will suggest the fastest option, disregarding the cost. When using balance, the state machine will choose between cost and speed as a compromise, depending upon the parameter balanced weight. Balanced weight is a linear weight between 0 and 1. It expresses the trade-off between cost and time. So 0 is equivalent to the speed strategy, and 1 is equivalent to the cost strategy. By default, this is set to 0.5. The auto-optimized parameters tell the state machine to apply the optimal configuration at the end of the execution. If you need to use an alias for your function, you can set this here too. Without these parameters, the tests will run and not make any changes at all to your Lambda function or your environment. Once the process is finished running, you'll see the results as a JSON output. The number here represents the recommended settings for the function tested based upon the input strategy. The visualization attribute shows an auto-generated URL. If you visit this, you'll be able to visualize and inspect average statistics about the cost and performance. These statistics are not shared beyond your browser, since all the data is encoded in a URL hash, which is only available on the client side. I'll show you some of the visualizations that the Power Tuning app can create. In this example, the x-axis is megabytes of memory, and the y-axis is execution time. The blue line represents cost, and the red line is execution time. So for this example, this shows that the fastest execution time is with 3008 megabytes of RAM, as this was the optimal setting for this function. But the lowest cost options were both 1024 megabytes and 1536 megabytes. So depending on whether your strategy was lowest cost or lowest speed, you could then set the RAM allocation for the function as needed. We've run the Lambda Power Tuning tool on thousands of different functions, so I wanted to share with you some real-life examples and visualizations. For a very simple function that runs quickly without interaction with other services, you'll often see this kind of graph. Since the executions always take under 100 milliseconds, but the billing is rounded up to 100 milliseconds, increasing the speed of the execution doesn't impact the cost. Similarly, adding memory will also proportionally increase the cost of the execution in this case. But it might be worth considering 256 megabytes. This can often be 3 to 5 times faster than 128 megabytes, so it depends on your use case. For a CPU-bound long-running algorithm, it looks a bit different. This function uses NumPy for compute-intensive calculations. At the 128 megabyte level, execution time is 9.5 seconds. This drops rapidly as memory is added. At 256 megabytes, the total time is just under 5 seconds, and at 1 gigabyte, it's just over 1 second. So in this case, the overall cost is fairly stable as memory increases, but performance improvements are up to 1 order of magnitude. It goes from 9 seconds to 900 milliseconds for just a 25% increase in cost. Here's another CPU-bound algorithm for calculating prime numbers. This is a very long-running algorithm taking up to 35 seconds. As memory is added, the speed increases, but the cost also decreases until 1.5 megabytes. On this graph, 1.5 megabytes is a great optimization since it improves both the speed and the cost. When you see a result like this, it's worth checking the lower memory bound with more granularity to see if it's even better at 1.3 megabytes or 1.7 megabytes. This is the same test as the previous graph, but run at 64 megabyte memory intervals, so it increases the granularity of the result. When we increase the power granularity, we can see that we can keep reducing cost and increasing speed up to 1.8 gigabytes. It's 0.5 seconds faster than 1.5 gigabytes for only about 2% of a cost increase. Switching gears, here's a function that's network bound. The function is making one third-party HTTP call. Now in this case, increasing the memory has a limited impact on execution time, but it's more expensive. This shows more or less the same performance across different power configurations. While 128 megabytes is always cheaper, sometimes it might be exploring other options up to 512 megabytes. Here it's 18% faster but 3 times more expensive, whereas 3 gigabytes is 20% faster but it's 30 times more expensive. So it really depends on the use case as to which configuration you should select. In this network-bound function, this makes 3 DynamoDB queries. Now until 512 megabytes, cost decreases, then it starts to increase at 1 gigabyte. This is because the execution speed is under 100 milliseconds, and billing is always rounded up to the nearest 100 milliseconds. So performance gets much better at 3 gigabytes, which is 60% faster, but it's 6 times more expensive. So in this case, 512 megabytes is a good trade-off between cost and speed. In another network-bound function, downloading a 150 megabyte object from S3, there's a 30% increase in speed from 512 megabytes to 1 gigabyte, though it's 50% more expensive. Then performance is very stable for higher values of power, so you're not seeing any additional benefit. But here, we can do even better by changing one single line of code and using a multi-threaded download. So with the multi-threaded download enabled, it's 45% faster and cheaper at 512 megabytes. And even the fastest, which is 3 gigabytes, is almost 4 times faster, is also 4 times cheaper than before the single-threaded version. And that's just with a one-line code change. So different types of functions yield different results in the Lambda Power Tuning tool, and the visualizations can help identify the best cost-speed trade-offs for your particular use case. You can often find that increasing the memory and therefore increasing the power can give you both a faster execution at a lower cost. But it really depends on the profile of the function, and if that function is memory bound, CPU bound, or network bound. So it's worth running the profiler to see the results. Once again, this is the URL where you can download this open source tool, but it's also available as a serverless application repo app. Just one final note on this, it's worth considering how billing impacts the final result. Billing rounds up to the nearest 100 milliseconds, so let's take a look at these two examples. In the first case, the invocation takes 480 milliseconds. So after a 15% improvement, it takes 408 milliseconds. But even with a 15% improvement, that's actually a 0% cost optimization, because in both cases, the billing is 500 milliseconds. In the second example, an invocation that takes 310 milliseconds, here a 5% performance improvement means that it now takes 294 milliseconds. But because the billing goes from 400 milliseconds to 300 milliseconds, this is actually a 25% cost optimization. So of course, the trade-off between speed and cost always depends on the use case. Okay, so in this final section, let's discuss some architecture and best practices. First, avoid monolithic functions. These are functions that contain everything in your application. It's better to have one function per purpose and enable specialization. There are some architectural benefits too as your applications develop. But the most immediate impact up front is reducing the deployment package size and improving the execution speed. Next, minify your code wherever possible to help get the package size as small as it can be. Also remember to lazily initialize shared libraries and objects, especially if you have multiple functions per file. And optimize your dependencies and imports. For example, we ran some tests and compared the results. If you need to use the DynamoDB SDK, include that specific package instead of the entire AWS SDK, and it can be 125 milliseconds faster. Similarly for X-Ray, adding -core to the package name parameter in the require saved 5 milliseconds. In a test with X-Ray for a single service, switching the method from capture AWS to the capture AWS client and providing the document DB client reference saved about 140 milliseconds. In each case, being more specific meant the code reference is a smaller package and it's faster to complete the init step. Going back to lazy initialization, here's a Python example. First, we import the Bodo3 module, and then we set two global variables for the S3 and DynamoDB clients. Now, if getObjects is called, the code checks to see if the S3 client object is initialized. If it's not, then it initializes it. And if getItems is called, the code checks to see if the DynamoDB client is initialized, and if not, that initializes it there too. Now, this is instead of initializing both objects in the init process, and this can make the individual function calls more responsive if you're sharing global objects across multiple functions. However, this is not better if you use provisioned concurrency, since the init code is completed long before the handlers are invoked. So many customers have petabytes of data in relational databases, so they need to use Lambda functions to access that data. And one of the problems is that relational databases are connection-based, and they're typically used with a pool of servers with long periods of uptime. So when you use Lambda functions that scale up, this can overwhelm the database with connection requests. And connections are just memory on database servers, so this can impact performance too. As Lambda functions are ephemeral, this kind of connection to a database is really not ideal. So at reInvent, we launched RDS Proxy as a solution to this problem. You simply point your Lambda code at the proxy instead of the database, and the proxy will intelligently manage the database connections. It can also make your applications more resilient to database failures and help improve your security posture thanks to some of the features bundled with this service. RDS Proxy is currently in preview, and we're seeing enormous popularity across customers with RDS databases. It's really easy to implement, and it can really help match the way that scalable compute works with traditional database architectures. Looking at some of the other best practices for performance and cost, there are a few other things worth discussing. The important thing to remember with Lambda is that you're charged when functions are running, so time matters. Eliminating unnecessary steps and reducing execution time also reduces your bill. So first, don't orchestrate within your Lambda function. If you have complex workflows, especially ones that take longer amounts of time, use step functions. This not only helps remove what I call spaghetti code from your functions, it helps make your workflows more resilient at scale, and it makes them easier to debug and also easier to modify and maintain in the future. It's easy to use and set up, and in many cases can be more cost-effective too by removing idle time from your Lambda functions. Transform, don't transport data. So if your function is simply moving data from one service to another, you might not need the Lambda function at all. There are other options for moving data around. For example, for API gateway to SQS or DynamoDB, you could use VTL and eliminate the function entirely. Services like EventBridge allow you to transform data flowing through the service too, so that can eliminate the need for a simple function that's only making minimal changes between inputs and outputs. Don't forget to use filters that cut down the number of events produced by your Lambda functions. In S3, you can use event prefixes and suffixes to only receive a subset of events based upon object names. With Amazon EventBridge, you can use powerful content filtering logic within the rules to be highly selective in which events trigger your functions. All of this reduces cost and efficiency because you're only invoking Lambda for the events that your application cares about. If your function makes HTTP requests, one very simple configuration change can improve performance by up to 70%. By default, the HTTP agents for many SDKs create a new TCP connection for every request. You can use the keep alive property so your function reuses this connection on warm starts. There's an environment variable for the SDK, or you can change the setting directly in your code. This example shows the code for Node.js, but there are examples for other runtimes too. In a simple test for a Lambda function querying DynamoDB, we saw that the first invocation took around 30 milliseconds, and then subsequent invocations took only 10 milliseconds after the keep alive flag was enabled. Just one thing to mention here, if you're using the AWS SDK bundled in Lambda, you'll need to import the newer version of the SDK into your Lambda package or as a layer, since this feature was added and introduced to a more recent version than the one bundled in Lambda. We recommend always bundling the SDK into your function code anyway, rather than depending on the version included in the Lambda service. This is a pretty major performance improvement for a very small change, so take a look at the bit.ly link for more information on how to use this in your applications. When it comes to performance of your entire application at scale, it's worth comparing synchronous and asynchronous approaches. We see many developers using synchronous design, especially when they first start building serverless applications. But in distributed computing and event-based architecture, often asynchronous design can give you better performance overall, both from an end-user perspective if you're building interactive workloads, and for throughput when your traffic scales up in production. AWS has a number of services that can help decouple parts of your application, like SQS or EventBridge. This can help prevent slower downstream processes from impacting faster upstream processes, and also make your upstream services more resilient to any service disruptions downstream. From a cost perspective, it can also reduce idle time in your Lambda functions, which reduces your AWS bill. Since many of us now work on complex applications that change frequently, the asynchronous approach can help here too, since the parts of the applications are more decoupled. Building asynchronous architectures is simplified in the AWS cloud by the number of different services we can use as serverless developers. It helps move the dependence from custom code in synchronous design into robust managed services instead. So what did we look at in this presentation? Well, we looked at cold starts and the causes of cold starts and what you can do to best minimize those. I explained some of the VPC improvements we've rolled out, and also the new feature, Provisioned Concurrency, that you can use to totally eliminate cold starts for your functions. Then we looked at memory and profiling. Remember, memory is power for Lambda, and you can use the AWS Lambda Power Tuning tool to find the best memory settings depending on the trade-offs for your particular Lambda functions. And we also looked at architecture and optimization, best practices including the use of RDS Proxy if you're using RDS databases, and using asynchronous design and service integration to avoid Lambda functions at all in some cases. So thanks for listening to this tech talk. My name's James Bezic. I'm a developer advocate for AWS Serverless. If you'd like to contact me, you can reach me at jbezic@amazon.com. Post your questions in the Q&A window, and we'll be happy to help. Thanks very much for your time.